Okay, so here we are, week 3, day 11, chapter 3, section 8. Whew, week 3, hard to believe. Okay, so this section we're going to look at what's called Newton's method. And Newton's method is just a way to solve a higher level equation that might be difficult to solve otherwise. So, for instance, if you have a graph, let's say this graph here, and you're looking at this and you're like, if I trace this on my graph, it looks like there's a 0 at this point about right here. How could you figure out whether or not that was the actual 0 or not? Now, you could zoom in and get a little closer, and then zoom in and get a little closer. And if you do that, what you'll find is that the answer is between 0.007 and 0.008. And there are computer programs and some fancy calculators that will figure those roots out for you. But before all that was discovered, what happened and how do those calculators work? What program do those calculators use? And they use a program, a lot of them, that was developed that's called Newton's method, also called Newton-Raphson method. Okay, so here's another example here. We have an f of x curve going up through. We would like to know what this 0 is. How could we find out what that is? Well, we know the f of x, and we could examine the slope at different points. So let's say I look at this tangent line at x1, and then I look at the slope of the tangent line. Well, I would have a point and a slope, and that would give me this equation. And I could do that to get closer to this by maybe examining this point. And that would get me closer to r. And then I might want to go even closer. Now, sometimes Newton's method won't work. I mean, you might get something that's kind of crazy right next to the 0, and it would end up giving you something completely wrong. But oftentimes Newton's method will work, and we're going to do a couple problems to take a look at that. But before we do that, let's do some reminders. Okay, so here we have point slope formula. Y minus y sub 1 equals the slope, or the first derivative, times x minus x sub 1. Now, Newton's method used this slope formula to determine that if we want to find out when y is equal to 0, if we want that y to be equal to 0, then we could solve to see how we can get closer. And we take this equation and simplify it, and we see that x2 would equal x1 minus the function divided by its derivative. So if I have a value already solved and I want to get a little bit closer, then I can use this method to get a little bit closer to that 0 until I get the answer for my 0, or very close to the answer. Here's a better figure over here, figure 3, that will demonstrate what I'm talking about. We want to find out where the root is, where r is. We have a point up here. Here's my x1. Here's my slope of my tangent line. This value doesn't really give me my value. Well, let's look at x2, getting a little bit closer. Tangent line over here comes through here. That's a little closer. Let's put that value in and go a little closer. So you can see each time I solve this, I get a value for y equals 0. But if I'm not on that line yet, I have to do it again and again until I get close to my root. Okay, now 4 is showing you how sometimes it could just be way off. So for example, let's say you wanted to find this value for the root here, and you started at this point, and this point is going to come way over here and intercept the x-axis. That's not very helpful. Nor is this one here. As I come down, it's still not going to work. So if I start here, do my slope of my tangent line, come here, do my slope of my tangent line, it's just going to end up being a mess. So doesn't always work, but does often work. So we're going to just take a little bit of a look at Newton's method and on a couple of the problems where it does work. First one is example 1, and this is on page 264. Okay. We have x cubed minus 2x minus 5 equals 0. Now, they tell us here to start at x equals 2. So they give us that first point that's close. And we want to figure out what the root is of this equation. Now, let's go back and re-examine that formula again. We can find x n plus 1 equals, if I have xn minus the function of x at n, or f at xn over the slope. Okay, so we're going to use Newton's method. Now, first thing I want to do is I want to put this value of x into my equation to see if that will help me at all and what kind of point it will give to me. So I put my x value in here, and when I do that, I will get 8 minus 4 minus 5, so 8 minus 9, which is negative 1. So I have a point 2, negative 1 that I can work with. The other thing that I need to do is, this is my f of x. I want to find my f prime of x, because that will give me my slope function. And I get 3x squared minus 2. Okay, so let's take a look at what we have. We want to find out x to the n plus 1. Let's go ahead and put this into our formula. When I have x sub n minus, here we go, x cubed n minus 2x n minus 5 over 3x squared n minus 2. And remember, the sub numbers just tells you what point you're looking at, whether you're looking at your first point, your second point, or your third point, etc. All right, now we want to take a look at when x equals 2. So if our x1 value, as they told us, is 2, then I'm going to put 2 in here. And I'm going to continue to put my function at the top and my derivative at the bottom. And my x2 value is going to be 2 minus this. Now, if I'm looking at the 2, I want to plug 2 in for all my x. Okay, so I guess I probably should have just put x1 here and then substituted everything in the second one. So let's look at that. 8 minus 4 minus 5. We already know the top is negative 1. And then on the bottom, 12 minus 2 is 10. So I have x sub 2 being, this is going to be negative 1/10. So a negative and a negative is a positive. So I will have 2.1 being my value. Okay, so let's go again, but this time let's go a little closer. So I'm going to take this value, which is my x2, and I'm going to use it to find x3. So x3 will equal 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5, all of that over 3 times 2.1 squared minus 2. Now, you're going to want to use a calculator to put this in. I will warn you, though, be very careful when you're putting these in the calculator. You're going to have to put parentheses and parentheses to make sure that your decimals are read correctly. Okay? Once you do that, this will become 2.0946. And in fact, this is accurate for my answer to the fourth decimal place. So 2.0946. Okay? So quick review. You're given the first point that you're going to look at. You use Newton's law, plug everything in. That'll get you a little bit closer. Use that value again until you feel that you are close enough to the answer that you want or the root value. Now we're going to take a look at example 2. Example 2 says we have the 6th root of 2. So if I asked you, okay, what's the 6th root of 2? And I want you to find Newton's method to solve it. So as you can see, this is not only used for just functions with values of x. You can take really tiny numbers, root numbers, and figure it out as well. Now, they give you a little more information here. Let's take a look. You want you to find it to the 8 decimal places. And the first thing that we want to observe is this. Now, this is the little tricky part. We want to find out what the value is of this. So that would mean that I want to find out if I take something and I take it to the 6th power and I subtract 2 from it, that I would get 0. Okay, so again, how you do that is if I have x equals 6th root of 2, I would take it to the 6th power and then subtract 2. That's how you do it algebraically. Or you could just think logically as well. I'm looking for the answer, so I want to take something to the 6th minus 2 and have 0. That would give me the answer. All right. So now I have my f of x, and let's take a look at my f prime of x. Well, this is my f of x. All right, f prime of x is 6x to the 5th, and my 2 is gone. Okay, so let's start with a value that we think might be close to the 6th root of 2. Well, if I had the 6th root of 1, it would be 1 in there. And if I had some other value that I could take 6 of, like 2 times 2 times 2 times 2 times 2 times 2 times 2, that would be in the middle. So I have to think about where it's close. And so I want to start, since I know the 6th root of 1 is 1, I want to start at 1 and see if that will be helpful. So my plug and chug formula is this. Have my function on the top and my derivative on the bottom. Okay, so if I'm going to start at 1, that means I'm going to have x2 equals x sub 1 minus x sub 1 to the 6th minus 2 over 6 times x sub 1 to the 5th. And if I plug all of those values in, I'm going to have 1 minus 1 to the 6th minus 2 over 6 times 1 to the 5th. And again, you'll want to use your calculator, but you will need to be careful when using a calculator so that you can get your decimals correct. The first time that I try this, I get 1.16666. Okay? That means I'm going to take that value and do it again. So my x3 is going to equal x2. So when I plug it in, 1.16 repeating minus 1.16 repeating to the 6th minus 2 over 6 times 1.16 repeating to the 5th. Again, being very careful with calculator, you're going to have to make sure you put parentheses here, and when you do that, you should get the value of 1.2644368. Do it again and use that value, my x sub 3 value, and I have 1.2644368 minus, big old bracket here, 1.2644368 to the 6th minus 2. 6 times 1.2644368 to the 5th. When I calculate that very carefully in my calculator, I would do this here and this here, and I will get the value of 1.2249707. So what you want to notice here is that your values are still changing, but they look like they're kind of getting closer to something. Because I started out with 1.1666, now 1.26444, now 1.2 is still the same, but now I'm at 249,707. So let's do it again. Let's try x to the 5th. I'm going to use my x to the 4 value. And that will be my 1.2249707 minus, here we go again, 1.2249707 to the 6th power minus 2. 6 times 1.2644368 to the 5th. All right. Now, again, very carefully, putting this in their calculator, I get 1 point. Oh, is it 1.1224? Hold on, let me double check this number here. I missed a 1 before, sorry. This is a 1 and this is a 1 right here in front. Okay, I miswrote it. All right, so 1.122499707 again. Nope, that's wrong. 1.12246205. Okay. Phew, those decimals are tricky. All right, now let's take x to the 6th. And I'm going to use my x to the 5. And when I plug this in, 1.122462205 minus, here we go, 1.22466205 to the 6th minus 2 over 6 times 1.122462205, and that is to the 5th. And this time, when I do it, after doing it 6 times, I will get the same thing 8 places as I got the last time. So that tells me that I am finished. Okay, let's see what else we have here. That is about it. We can do it with trig functions as well. This will show you one that is done with the cosine, looking at the cosine x equals x. And again, you just continue to do it until you get to a point where you're getting the same value. That way that you know that you are close enough to the accuracy that you want. All right, well, that is it for section 3.8, and I'll see you in a few minutes for section 3.9.